morning and welcome to today's electronic design webcast. Our topic today is signal generator phase noise and measuring the ENOB of high-speed ADCs. It's sponsored by Anritsu. I'm Alex Pault. I'm the editor-at-large with Endeavor Business Media's Design and Engineering Group. Now, before we start, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your question or your issue into the Ask a Question box, and a member of our team will assist you. You can also click on the question mark Help button in the upper right corner of the screen. Additionally, we welcome your questions to today's event, of course. We'll answer any of the questions that we have time for during the event, and we will follow up with any of you who have questions for us. Please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click the Send button. If you'd like a copy of the presentation, please click on the Event Resources button on the side of the screen to download the presentation. Please be aware that today's session is being recorded, and it will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now, let's meet today's speaker. Sadashiv Phadnis is the Product Marketing Manager for signal generators, power meters, and components at Anritsu in Morgan Hill, California. Now, Sadashiv has more than 30 years of experience in RF design and product marketing, and that includes the design of satellite receivers, synthesizers, and LNAs. So, hey, Sadashiv, it's really nice to see you today. I'm glad you're here.
Thank you, and hello, everyone. Alex, it's really great to be talking to you on today's topic of why phase noise of signal generators is by far the most important factor while measuring the ENOB of high-speed ADCs.
Well, Sadashiv, before we dive into that measurement topic, I think it might be good if you gave us a overview of some high-speed ADC applications and some of the performance parameters that are critical in those applications.
Thanks, Alec. Actually, that's a great place to start, in fact. And to facilitate our discussion, I have prepared a few slides, and I would like to start with this particular one. Let me bring it up. Okay, so the high-speed ADCs, have seen a remarkable improvement in the last few years. ADCs with sampling rate more than 10 gigasamples are offered by several vendors today. High-speed ADCs drive digitization of signals closer to the antenna than ever before. In the past, they used to use the ADCs for digitizing IF signals, but now they are much closer to the antenna. They are used for digitization of RF signals as well, right? And then the high-speed ADCs drive instruments such as digital storage oscilloscopes to higher frequencies than ever before. So those two are, I can easily point out those two big applications of high-speed ADCs. Now, in the receivers, what does the digitization do? And, after the RF or IF signals are digitized in the receivers, they enable designers to use sophisticated DSP techniques to achieve simultaneous reception of multiple signals, fast channel acquisition, and so on and so forth. And for the digital storage oscilloscopes, ADC are really central to the instrument as overall. They convert the analog signals, and then the distortions and the noise are analyzed and displayed, right? So in both cases, ADCs play a central role. And ADC's inherent noise and the resulting SNR at the output is critical for both these applications, for both digital storage oscilloscope application and as well as digital receivers application.
Well, That's very interesting. You mentioned that, the importance of the signal-to-noise ratio at the ADC's output, but how is that related? How is that related to the ENOB of the ADC, which is,
Good question.
our discussion.
Yes. Good question. So actually, the SNR at the output of ADCs is a function of number of ADC bits, right, or the resolution of ADCs, so to speak. And I have advanced to the next slide here, and we show a relationship between SNR and the resolution of ADCs here. So, for example, an 8-bit ADC has an SNR of 50 dB, and 10-bit ADC has 62 dB, and so on and so forth. But this relationship is theoretical in the sense that it takes only quantization noise into account. But if you were to measure real SNR at the output of ADC, it would be influenced by ADC's inherent noise contributions, like the internal thermal noise, non-linearities of ADC within ADC, and the aperture jitter in the clock path, right? So there are internal contributions that really make this SNR lower than the theoretical number that's shown here, right? Now, the thing is, you take this real SNR and then convert it back to number of bits. That is what we call as effective number of bits, which are ENOB, for instance, right? That's what we are talking about here. Yeah, I think that's it. Yeah.
Okay. Now, familiar us with the typical ENOB measurement setups of ADCs and how the SNR of measuring instruments contribute to the measurement accuracy.
Yes. So as I told you, as I mentioned, there are ADCs ADCs inherent noise contributors. But when you are measuring SNR at the output of ADC, the external measuring equipment also contributes to the SNR at the output of ADC. And let me explain, let me take you to the next slide that explains it a bit better. So if you want to measure SNR at the output of ADCs and indirectly ENOB, right, at the output of ADCs, you need two signal generators, one to supply a pure sinusoid at the input of ADC, and another signal source to drive the clock of the ADC. And now, and at the output of ADC, whatever is converted, whatever is digitized, you capture that and you apply FFT or some other data analysis means in order to calculate the signal to noise ratio. This is what the typical setup looks like to measure SNR or the ENOB of ADCs. Now, the SNR at the output of ADCs is a sum of three SNRs, as you can see here. Of course, there is SNR, there is inherent SNR of ADC, and then there are SNRs contributed by each of the signal sources. And when you take a sum of all this, that's the SNR you are measuring at the output of ADC. So clearly, the lower the noise contributed by each of the sources, the closer you are going to be to the inherent SNR of the ADC, while you're making measurement. And then you take that real SNR measurement and then convert that into number of bits, and that would give you effective number of bits. Now there is another slide that there is another setup which is pretty similar also with the previous one, which is applicable more for the digital storage oscilloscopes. And in this case, the digital storage oscilloscopes have their own clock, so you don't need the second signal generator. You just need the signal generator that supplies a clean sinusoid input into the oscilloscope, and then you make a measurement. But all other components of the measurement setup remain the same. You still capture the digital data and do an FFT and do some data analysis to come up with an SNR and then calculate back the effective number of bits. And the critical performance parameters for measurement for both for the ADC and also DSO in this case is integrated phase noise and spurious over the entire frequency range of the DSO, and harmonics and subharmonics over entire input frequency range of the DSO. Those two factors.
Now, what about the performance parameters of the analog sources? How they influence the signal-to-noise ratio?
Yes. So again, let me go back to one of my previous slides here. As I mentioned here, the SNR at the output of the ADC is a function of 3 SNRs, right? Which is a sum of 3 SNRs. That is the inherent ADC, which is what you want to measure. But there is also contribution from SNR of each of these sources. Now, if you want to get very, very close to the real SNR of ADC, which is the inherent SNR of ADC, then obviously the signal-to-noise ratio of your signal sources have to be much higher than ADC's SNR, so that they do not contribute much. That is the factor. That is the single most important factor for the signal sources that are used for ADCs. Now, what determines the SNR of each of these signal sources? Phase noise. I would say phase noise. That's the single most important factor that would determine the SNR. And not just the phase noise, that's actually the integrated phase noise from a certain lower limit to a certain higher frequency limit. Now, the lower limit that's used for integration is different. Both the lower and the higher limits used for integration are different for clock and for signal sources. Now, for clock sources, it is typically between 10 kilohertz. The lower limit is 10 kilohertz. And the upper limit is equal to the bandwidth in the clock path, right? And for the signal sources, the lower limit of integration is somewhere between 1 kilohertz and 10 kilohertz, and that's more application dependent. If you are using it in a receiver, then your clock recovery bandwidth or the symbol recovery bandwidth determines what your lower limit is, because at frequencies lower than that bandwidth, essentially the receiver cuts off the phase noise, so it wouldn't be important. And then the higher limit and the upper limit really is the Nike bandwidth. So the lower limit of integration is dependent on the application. And for receiver chains, it's close to as I said, it's close to the carrier and timing recovery loop bandwidths, as they act as high-pass filters for phase noise.
Right. Now, since phase noise is so critical in ENOB measurements, what are your thoughts on phase noise performance of signal generators available today?
Yeah, so there are some great signal generators available in the market today. And I would like to specifically talk about a signal generator that we introduced. Anritsu has introduced recently, I think, in the second week of November. We introduced our new signal generator called Rubidium. And let me quickly take you to a slide that shows the phase noise performance of Rubidium versus a typical competitor signal generator. Rubidium essentially kind of establishes a new milestone in terms of phase noise performance, and phase noise in turn determines the SNR in this application, in this measurement applications, where you want to measure ENOB of ADCs, right? And in this slide, you can really see the difference in performance of Rubidium versus the competition, right? Now let me again go back to my previous slide. Why does it matter? As you can see here, when you are integrating the phase noise, the signal generator with a tighter phase noise profile obviously is going to give you much better SNR than a signal generator with a broader phase noise profile. And this slide quantifies that, right? It shows you, for example, I've given two typical measurements, one at 10 kilohertz offset and one at 10 megahertz offset, and both were the measurements done at 10 gigahertz, output of the signal generator. And you can see the difference here, that a typical signal generator would give you something like a standard signal generator would give you something like minus 120 dBc per hertz, whereas rubidium, gives you minus 132. So it's almost like a 10 dB difference between what is out there in the market and what rubidium provides. And this is a plot, that shows the difference. You can see here the delta of 10 dB in the pedestal region, in the flat region. This is what is called as the pedestal region, and this region is actually extends from somewhere between 1 to 10 kilohertz and all the way up to 10 megahertz or even higher, right? And as I mentioned before in one of my slides, and this is precisely the region where you would want best performance, best phase noise performance for measuring ENOP, right? This is where you need your best phase noise. And this is where rubidium actually performs the best, right? I can also show some of the measurements plots also for low phase noise options. Besides the standard version, we also provide 2 or 3 tiers of low phase noise options, and with every tier we maintain that 10 dB difference. So that means rubidium, if you use rubidium as signal generator for measuring the ENOB of ADCs, it allows you to do, say, 2 things specifically, right? It allows you to measure either measure ENOB more accurately, right, for a given resolution, or it allows you to measure higher ENOB of higher resolution ADC. So it allows you to do one or both of these things, right? There is one more thing that I wanted to mention specifically. We have a very special low noise option that provides kind of a unprecedented phase noise performance in this 1 kilohertz to 10 megahertz range, which is minus 140 dBc. And this, I think, is particularly suitable for driving the ADC clocks, because the integrated phase noise, which in turn determines the clock jitter, you would get probably the best clock jitter performance with this option, this one. So just to summarize, right, the great phase noise option that rubidium offers, allows users to do 2 things. One is they can measure SNRs with better accuracy for a given resolution, or they can measure SNRs of higher resolution ADCs for the same accuracy. So it's one of the 2.
Wow, that's very interesting. Now, I really appreciate that presentation, and I know our audience did as well. So let's get the audience involved in this. Let's take some of their questions. And frankly, I have, if we have some time, I have 1 or 2 of my own, but let's give the audience some priority first. And for anyone who hasn't put in a question yet, please type in a question in the box. And like I said, we'll take care of you. So the first question is, does phase noise at lower frequency Oh, does phase noise at lower frequency offsets contribute more to overall integrated phase noise than phase noise at higher offsets?
Good question. Yeah, so it would appear as though, the phase noise at lower offsets would contribute more. But what happens is at lower offsets, when you integrate, phase noise, your integration base is much smaller. Like, for instance, if you are integrating between 10 kilohertz and 1 kilohertz, even though the phase noise is higher, the base is much smaller. It's 10 minus 1, so somewhere in 9 kilohertz. Now, at higher offsets, for example, between 100 kilohertz and 10 megahertz, right? Now, in this range, the phase noise is much smaller, but your integration base is much larger. It's let's say 10 megahertz minus 100 kilohertz, almost 10 megahertz. It's that much more larger. So in general, what I would say is the phase noise in the mid region, which I said the pedestal region, where the phase noise flattens, that region contributes the least to the overall integrated phase noise, and on either side of it, pretty much the same, right? So there is equal contribution between phase noise at lower offsets and phase noise at higher offsets.
Good answer. Now, then I believe our questioner probably got satisfied with that one. Let's go to the next question. Does harmonic performance of the analog source used to drive the clock contribute to the ENOB measurement?
No, not really, because you in the clock path, what you really care about is the zero crossings, right? And really, the second and the third harmonics do not contribute to the zero crossings at all. So harmonics is the least factor. And the second thing is, usually within these ADC devices, they amplify the clock signal and make it a square rather than a sinusoid. So harmonics exist as it is, but they really do not contribute anything to the ENOB. Yeah.
Got it. So actually, I think that's related to one of the next question that we've got here. How does spurious performance affect ENOB measurement?
Yes. So spurious performance would be much more important, I would say, right, than harmonics. And the reason is because spurious is unpredictable. It's not very easy to filter out spurious, right? And that's why spurious performance matters much more than harmonics. And now, even in this case, rubidium's spurious performance is exemplary. It's much lower than any of the competitors, and rubidium really offers the best value, I would say, in terms of measuring ENOB.
Got it. Well, we've got a couple of other questions, but frankly, I'm going to take the opportunity. I've given the audience a chance. I want to ask you a couple of things about this myself, because frankly, I wanted to get a little bit more big picture with you for a half a second, and use the questions as an opportunity. I've always been an audiophile and a watch collector, and time and signal and phase have always been important to me in all of these aspects. And I'd like you to talk about how you think about the relationship. Once upon a time, the only people who cared about jitter were digital audio people. And now jitter is critical in everything. Noise.
Right.
Noise is critical in everything. So I'd like you to tell me your this whole interrelation, internet time, phase noise, all of these things within the cloud. It's a really big juggling act, isn't it?
Yes, correct. I mean, jitter is really is one of the fundamental performance parameters for many of these things. For example, these signal generators could be used as a clock sources for many of the high-speed communication networks, right, where jitter is absolutely critical, right? And you mentioned the timing signal on the internet, and what that drives is also a clock, and its jitter is a critical factor there as well, right? So jitter is really fundamental to many things today, because there is so much of digitization that has happened, right?
Yeah, I agree. Actually, I think we inspired a question. We've got someone asking, do you have any device suggestions to reduce jitter and lag in advanced systems?
Actually, many of the semiconductor vendors do offer devices to reduce jitter. So typically, they act as intermediate clock receivers. They receive a clock, then clean it up, and then output it for further transmitters. So there are many semiconductor vendors that do offer that kind of solution. Yes.
Well, it really is becoming a very interrelated situation. What would you say the software impact on this whole equation is? Because a lot of the people out there are hardware engineers trying to develop advanced solutions that are bridging both worlds today. Do you have any advice for those people?
Yes, so software comes into picture in a couple of places, right? So one is when you capture the digital data. For example, I mentioned you perform an FFT, and FFT nowadays is done either in software or hardware, right? So when it is done in software, that's where the DSP algorithms become very critical, right? And then once the FFT is done, there is a lot of analysis that's done on top of it in order to extract the noise components, the distortion components, and then either displayed in the case of storage oscilloscopes, or analyzed further in the case of receivers, to demodulate the signal and get the necessary bit error rates. So of course, software is critical. It plays an extremely important role. But all that can happen only after digitization, right? So obviously, ADCs are at the center of it all, I would say.
Well, you got to have the signal. And the ADCs are the connection between the digital and the analog world.
Absolutely. Yeah. And we want them to perform the way they should perform. And, making ENOB measurements is absolutely important. Yeah.
I couldn't agree more. It looks like I accidentally ran our clock out. We're going to have to answer the rest of the questions after the event. We've run out of time. For the questions that we did not get a chance to answer, we will be getting back to you all via email, I promise. So that concludes today's presentation. And on behalf of Electronic Design, I'd like to thank Anritsu for sponsoring the event. And I would like to thank you for giving it. And of course, all of you out there for joining us. Have a great day.
Thank you, Alex. Thank you, Alex.
Thank you, everyone.